Let's graph the area underneath this function, x times the floor of the square root of x. Since we're taking the square root of x and finding the floor, we're going to look at intervals between consecutive perfect squares. So if x is in the interval between 1 and 4, we have the floor of the square root is equal to 1, so our function becomes y equals x. Between the next two consecutive squares, 4 and 9, the floor of this square root is equal to 2, and so y is equal to 2x, and so on. So between consecutive perfect squares, we have lines with increasing slope. And if we graph them, between x equals 1 and 4, y is between 1 and 4. And between 4 and 9, y goes from 8 to 18. And this last interval, y goes from 27 to 48, and so on. So we're summing up the area of these trapezoids between these integers. So as we go from a sub n and add on the next trapezoid at a of n plus 1, we're going to add in this difference, which is the area of the trapezoid between x equals n and x equals n plus 1. Each of these trapezoids has a height measured in the horizontal direction of 1, and the bases, which are vertical, are the y-coordinates of consecutive integers. The base on the left-hand side is the y-coordinate n times the floor of the square root of n, and on the right-hand side, our x-coordinate is n plus 1, and this coefficient is the same. So let's find the area of these narrow trapezoids between consecutive integers. Here's our formula for the area of that trapezoid, and we'll substitute, and we'll factor and collect like terms. We'll notice that this middle factor is odd. Since we're looking for areas that are integers, we need to be able to cancel this 1/2. That happens if this last factor is even. So when the floor of the square root is even, then our next trapezoid is going to have an area that is an integer. We'll abbreviate integers with a z. And likewise, if our floor function is odd, we'll be adding on an area that looks like a fraction with a denominator of 2. If our previous area was also a fraction with a denominator of 2, then our new area is going to be an integer. And if our old area was an integer, and we're adding on another area that's an integer, we're going to create a of n plus 1 that's also an integer. Let's write out these cases. Our new area is going to be our old area plus the area of the trapezoid. So if this factor is even, and our previous area was an integer, then the next area is also going to be an integer. If our previous area was not an integer, then our next area is also not going to be an integer. So when this factor is even, we're going to have no change between consecutive a sub n's. When this factor is odd, if the previous area was an integer, we're going to be adding this fraction with a denominator to it. So our new area is not going to be an integer. But if our previous area was not an integer, then it was a fraction over 2. We'll be adding another fraction with 2 in the denominator, and this will give us an area that is an integer. So when this factor is odd, we're going to switch one way or the other, with one area being an integer and the other one isn't. Let's see this in action with some examples. Our first value for this factor is 1, which is odd. This is true for n equals 1, 2, or 3. Our first area, a sub 1, is just going to be the average of the bases. This area is 3/2 and not an integer. To find a of 2, we're going to take a of 1 and add the next trapezoid with bases 2 and 3. We're going to add 3/2 and 5/2 and get 4, and this is an integer. With a of 3, we're going to be adding a fraction with 2 in the denominator, and a2 is an integer, so a3 is not. In this first interval, we have 1n for which a sub n is an integer. Let's see what happens when this factor is equal to 2, which is even. Recall that when this factor is even, we're going to have no change between consecutive areas from being an integer to not, or vice versa. This factor is equal to 2 for n in the interval between 4 and 8. Since a sub 3 is not an integer, and when this factor is even, it leaves that status unchanged. We're going to have all a of n in this interval is also not an integer. So we'll have no valid areas in this interval. The next value of this factor is odd, which means we're now going to be changing whether it's an integer or not on alternating areas. This is for n between 9 and 15. From the previous interval, since a8 is not an integer, this means that a9 will be. a10 won't, but a11 is an integer, so is a13 and a15. So in this interval, we have 4 areas that are integers. When this factor factor is 4. This is even. This is going to leave the areas unchanged. Since A15 is an integer, everything in this next interval is also going to be an integer. And that's 9 more valid areas. Let's put this information into a table and see if we can see a pattern. We'll keep track of the value of this floor function, the number of n's in this interval. So for example, when this factor is equal to 1, we have 3 valid values of n. We'll count the number of areas that are integers. In this example, we had 1 in this case. And then we'll keep track of whether the last area in this interval was an integer or not. Continuing, when this factor is 2, we had 5 values of n in this interval, but none of them were integers, including a sub 8. When the factor is equal to 3, the number of values of n in this interval is 7. And we note the pattern here. There's always an odd number between consecutive squares. So this column is going to be consecutive odd numbers. Here, because the factor is odd, we're going to alternate between integer and non-integer, and we found 4 of them here, including the last one, a of 15, which means when the next one is even, for these 9 values, all of them are going to be integers. Because this is even, it's going to leave this last area unchanged. Let's see if we can repeat this and go a little bit faster. Our next floor is 5. We're going to have 11 numbers in this interval. We're going to alternate between integers and non-integers because this factor is odd. We start off with an area that is an integer, so our first one in this interval will not be an integer, so we'll have 5 of them here. It might be helpful to keep track of the parity of n. In this first category, a was an integer when n was even. Here we have nothing. Here we have odd values of n. So this is half of these values of n rounding up. And then when this factor is 4, all of them are integers. When the factor is 5, again, we're alternating. These 5 are all the even values of n, as we had up here. And let's continue with 6. We have 13 values of n here. Since a35 wasn't an integer, and we're leaving that unchanged, this is 0 again. The last area in this interval is a48, which is not an integer. The next interval, 7, has 15. Since it's odd, we're going to begin with a of 49, which will be an integer, and all the other odd n's in this interval. So we're taking half of these and rounding up. That'll give us 8, including a of 63. The next interval has 17 valid n's. Since a of 63 is an integer and this factor is even, then all 17 of these are going to be integers as well, including the last one. And now I think we can see our pattern repeats every 4. I think we can convince ourselves of that because this second column consists of consecutive odd numbers. The parity is going to be consistent every 4 rows. Here, the total number of valid an's in the first 4 rows is 14. The total in the second 4 rows is going to be 14 plus another 16. And I think we can see that because this 16 consists of 8 additional valid areas in the 4th row in each group of 4. And then we get 4 more in row 5 and 4 more in row 7 than we did in rows 1 and 3 respectively, because the size of these intervals is also growing as an arithmetic progression. So now I think we can simplify our counting. If we combine our intervals to have a length of 4 for our floor function, the number of areas that are integers is going to grow in an arithmetic progression. So this interval refers to the first 4 rows of the previous table. We had 14 valid areas. The next 4 rows has this factor between 5 and 8. The next interval is between 9 and 12, and we're going to add another 16 to that. Let's figure out when we can stop. We're looking for n that is less than 1,000. 1,000 is between these 2 consecutive squares, so the floor of the square root of 1,000 is going to be equal to 31. So let's continue these intervals until we're in the neighborhood of 31. The smallest multiple of 4 that's less than 31 is 28. Counting the multiples of 4 here, this is going to be our 7th term. So this is 14 plus 16 times 6. Let's go ahead and add up all of these first, and then we'll take care of the last few intervals. This first part gives us 434 valid areas. Now let's check carefully as we approach n equals 1,000. After 28, we'll go on to 29. We'll have 59 valid values of n, which give us this floor function. Since we're looking at even values of n that give us an area that's an integer, we'll take half of the n and round down. This gives us 29 more. When this floor function is equal to 30, we have 61 values, the next odd number after 59, but we don't get anything in this interval. When our floor is equal to 31, that's going to be our last, but we only want n less than or equal to 1,000. Also, the way we calculate our areas, a sub n determines the area of the trapezoid to the right. So that last trapezoid occurs when n is equal to 999. So here, instead of including all the odd numbers between consecutive squares, we're going to look at the odd numbers between 31 squared and 999. So that's only 39 valid values of n. In the third row of each group of 4, we're looking for the odd values of n. So we're going to take half of this quantity and round up, which will give us 20 more. And those are our last trapezoids. So we've got these 434, and then we're going to add 29 and 20. And the answer is 483. If you'd like me to solve any other contest problems, please leave them in the comments.